Okay, this lecture is on Chapter 17, Section 4, and we're looking at how to evaluate and deal with chemical hazards. And we come across some terms that are definitely going to be important for the AP exam. The first of which is toxicology, which is the study of the harmful effects of chemicals on humans and other organisms. Basically, we're talking about the study of poisons. Toxicity is the measure of how harmful a substance is, its ability to cause injury, illness, or death to a person or a living organism. And the basic principle of toxicology, is that any synthetic or natural chemical can be harmful if ingested in a large enough quantity. Even something as simple as water, sugar, those things can become toxic. Again, it just depends on the amount ingested. So typically, we don't ingest enough sugar or water that it would actually be detrimental to our health. Whereas other chemicals in very, very tiny quantities could be, like cyanide. So the basic question that we come up with in toxicology is at what level of exposure to a particular toxin are there going to be harmful reactions? And so that's really what we're looking at here. We're going to look at some ways that scientists do this and determine what safe dosing is. So what about a dose? A dose is the amount a person has ingested, inhaled, or absorbed. Doesn't have to be a person, but in our case, we're going to be talking about people. There are some things that will affect the toxicity besides just the amount that you take. Your age, usually there's going to be a greater effect on children, and that's why there are certain medications that are not on the market for especially infants, but even for small children. Body size is the huge factor there. Children are just much, much smaller, so there's a greater effect on them. Genetic makeup, it can determine your sensitivity. Certain people are allergic to certain compounds, and that's just part of their nature, part of their DNA. You also have what's called multiple chemical sensitivity, MCS, and that's your body's ability to detoxify. Specifically, it's your liver, your lungs, and your kidneys. But you might hear on some drug commercials things like you should not take while undergoing treatment with an MAOI inhibitor. And again, what they're looking at is that certain chemicals will act together and overload your body's detox systems, and especially, again, your liver. If your liver can't detoxify, then you will actually become septic. You'll have a problem with your liver will become toxic, and that'll be the end of it. And then the next thing we've got is solubility and persistence. You have some substances, that are water soluble, and they'll come out of your body fairly quickly. If you drink enough water, things like salt are going to come out. And then there's things that are oil and fat soluble. This is like our DDT and our mercury, and that's why they don't come out. Once you have ingested them and they become part of your oil fat tissues, they stay in there forever, because you're not going to just rinse them out with water, which is what most of our body is made of. And so again, that's where biomagnification comes into play. There are many factors, again, that are determining those harmful effects. So first we talk about dose, now we talk about response, and it's what we call the dose response, sort of like cause effect. Response is the damage that results from the exposure to a chemical. And we can talk about it in two terms, being acute effect, immediate, rapid, harmful reaction, and chronic, permanent, or long-lasting. Now, an acute effect could be small, like just dizziness or nausea, or it could be fatal, like death. Same thing with your chronic effects. Usually, you're going to have chronic effects that are going to lead to death, but that's not always the case. You could have something chronic like arthritis that goes on and on and on, but never causes you enough harm to kill you. But the two here definitely could, liver damage and cancer. Again, they're permanent, long lasting. So it has nothing to do with how much it hurts, has nothing to do with whether or not you're going to die. It simply has to do with how fast. Acute effects come on quick and they go away fast. Chronic effects, long, long lasting. And here we've just got another graphic showing you some exposures that we get. And again, you would have to model those. That's what the computer is showing there. But you've got nutrition and food, pesticides, air pollution, soil, your genetic predisposition, I'm not going to read them all, but you get the idea. All of these things have an effect on how you particularly will react to any substance. And so it could be a medicine. It could be, some people who can take one Advil and that's fine, and other people take 3 or 4 to have to get the same effect. So again, part of that has to do with our own dispositions, with our own exposures, with everything that goes on within us. Our book looks specifically at children because, again, infants and children are more likely to have a toxic, lasting reaction. More likely, it says, to be susceptible to those effects. And here's the reasons why: they eat, drink, and breathe more per unit of body area than adults. So again, kids are going to breathe deep, they're going to breathe heavy, and they're very, very small. And so that's a lot of intake of pollutions that are coming in. Same thing with the eating and the drinking. If you've ever seen a child eat, they can eat just about as much as an adult because they're growing kids, but they've got a smaller body size. So they're burning it up faster, but again, they're inputting more pollutants per unit of body weight. Little kids put their fingers in their mouths all the time. Infants all the way up to, even elementary schoolers and upper elementary schoolers. But they're constantly fidgeting and putting their hands on the desk and putting them in their mouth. And if you think about all the different exposures that's going to create, there's a lot of toxins that can get picked up that way. And then lastly, they have a less well-developed immune system and body detoxification process. Your body does learn how to fight off diseases by getting diseases. So one of the tricks of parenting is that you let your child be exposed to a lot of things early on, and they're less likely to have severe reactions later. It's the kid who's kept away from dogs that gets a dog allergy. The kid who's born into a house with dogs and cats and dirt and gardens, those are the kids who are going to have a lot stronger immune systems because they get slowly inundated, their system becomes accustomed to it. Okay, so we talked about dose, we talked about response. And what we can do with that is called a dose-response curve. And scientists will do this with a test population. They will give certain doses to a variety of organisms, and they will see what the response is. An LD50 curve is a particular dose-response curve where they're looking to see what the average median dose is that will kill half of the population. So what you're seeing with LD50 is lethal dose that kills 50% of the population. And so anytime you see a graph that's supposed to be an LD50 graph, all you have to do is go up on the left side to 50% of the population, see what dose killed 50%. Now, an LD50 is not a target number. We don't want to kill 50% of the people who take a drug. We want to kill far less, but that is a side effect that's likely to happen. But again, think about if this was Advil. Would you really want to know that the median lethal dose for Advil was 70 pills? That if you take 70 pills, there's a 50% chance that you die, and I don't know if those numbers are accurate. But that's what the LD50 is meant to say, is this is the amount that will kill half of the population. There's 2 different types of models. There's a non-threshold dose response and a threshold dose response. And we're going to talk about what that is in a second. But the basics are a non-threshold dose response. You start to see effects with the first very, very small dose. A threshold dose response, you can take in a little bit and there's no effect at all. But then there's a threshold, and once you pass that threshold, you start to see effects. Maybe think about it as you can drink 1 can of Coke and it doesn't keep you up any later. But if you have that second can of Coke, the extra caffeine, all of a sudden you're staying up until midnight or 1. I'm an adult, so for me it's, I stayed up till 10. Okay, but anyway, we do these things, and we typically do them with smaller animals, maybe bacteria. Rats are a likely test subject. Even primates have been used. And then we have to make extrapolations to humans, because we don't want to go around killing 50% of our test subjects if they're human beings. And we'll talk about some other ways that you can do this besides animals. There are more humane methods than using animals. We can use computer simulations. We know enough about chemistry now that those tend to be fairly accurate. We can do tissue cultures or use individual animal cells to see what type of exposure would kill off just a cell. And we use a lot of chicken egg membranes. And so again, we don't always have to use animals. Tends to be, though, that people really do want that extra security of knowing that this was tested on another living organism, not just a computer model. The other thing that we don't know is the effects of mixtures of toxic chemicals. And sometimes we don't know this until after a drug has been on the market, that you simply cannot take a certain class of drugs with, again, those MAOI inhibitors. We didn't know that until people started to get the drugs, people started to die from those interactions. And so there are definitely some flaws. We cannot test every combination. So here's an LD50 graph. It's again hypothetical, but what you will see here is that you have the dose on the x-axis. So here we have given hypothetical units, so let's say it's milligrams. We give 0 milligrams right here. We give 2 milligrams, 4 milligrams, 6 milligrams, 8 milligrams, and so on. Again, if you want to find the LD50, we're going to go up to the percent of the population that's killed. So if we go up here to 50%, then we can go over and find that intersection, and we see that that intersection occurs at, down here on the x-axis, 7 milligrams. So our LD50 is going to be recorded as the dose, 7 milligrams. Okay, so again, this is an LD50 curve, and you can tell by this curve that you get 0 deaths all the way up here to a 3. So this would be a threshold model, because at 0, at 0, 1, or 2, or even 3, you get no negative effects. You get no response. So there's a threshold at 3, after which you start to see a response. So your steps here are listed on the side, are good to remember. First thing you want to do is find the 50% mark on the y-axis. Then you're going to draw a horizontal line until it hits the curve. My lines didn't match up exactly, but you'll forgive me. Then draw a perpendicular line straight down to the x-axis. And there you go. You get your x value on the lethal dose. Again, on this graph, it's going to be 7 units. And here's a list of how we classify toxicity. You'll see super toxic things are less than 5 milligrams per kilogram of body weight. So lethal dose, it says less than 7 drops. Nerve gas is botulism, mushroom toxin. Why somebody would inject botulism into their face to cure wrinkles, I don't know, because less than 7 drops ingested will kill you. Extremely toxic, you're talking 7 drops to a teaspoon. You see cyanide, heroin, parathion, that's like a pesticide flea dip thing, nicotine, okay? So when we talk about nicotine in cigarettes, it is an extremely toxic chemical. Very toxic, mercury, salt, morphine, codeine, recognize some of those as drug names. Moderately toxic, lead salts, DDT, sodium fluoride, caffeine. Slightly toxic, ethyl alcohol, Lysol, soap. So, if you see a kid drinking a little bit of Lysol out of the cupboard because he's a baby, he didn't know any better, as long as he didn't drink a pint to a quart, then, he's probably going to be okay. Sick, needs to go to the hospital, be monitored. But again, takes a lot of that type of thing to kill somebody. Essentially non-toxic, you see water, glycerin, table sugar. You have to have more than a quart of table sugar to have a lethal dose. The water glycerin thing, if you think about what that is, that's bubble solution. So if a kid drinks bubble solution, that's why it can say non-toxic on there. Again, essentially non-toxic. So again, this is just a little introduction. Tomorrow in class, you will be working with some toxicity ratings for other common household items. So what's the toxicity of your deodorant or of cough syrup? Those are some of the items we're going to look at and see for you at your body weight, how much of that substance would you need to ingest? Okay, so looking at those 2 types of dose response curves, again, we've got threshold and non-threshold. The question is, do you see adverse effects right away or after an overdose is what we would call it. Because remember, we don't want people to die from taking any of these drugs. We don't want somebody to die taking Advil. We don't want somebody to die because they were prescribed Lipitor. So on our two graphs here, what you'll see right here, this is called a no threshold. You start to see effects right away. Linear dose response curve would go this way. A lot of what we see, like we saw in the last graph, are non-linear dose response curves where you get minor effects and then it builds up suddenly. So again, this is more typical, which is why it's a solid line. But again, the idea with non-threshold is that we start to see results right away. For a threshold, we don't see any response, nothing negative, nobody's dying, everything looks good until you hit a certain level. And so this would be considered an overdose. So they tell you to take between 0 and 2 Advils. You take 4, you're still okay. You take 6, you're still okay. But at some point, and again, I don't know what the number is, at some point you overdose. And so that means you've gone over that threshold where there is no longer safety. Again, there's other ways that we can use, because we don't always want to use people, we don't always want to use animals. We use case reports to figure out what causes illnesses and what drugs are interacting with others, and epidemiological studies, so studying diseases. There are limitations though. There's too few people tested. It takes a long time to get all your results. And it's also very hard because when you've got people involved, you have other factors, other variables at play. It's very difficult with toxicology, with environmental sciences, to be able to control for everything. And you can't use it for new hazards. We can't just develop a new product and say, well, let's go test it on some people and see what happens, because that's incredibly dangerous and unethical. One of my favorite graphics in your book, and it's incredibly scary, is looking at all of the different toxins that are in your house. And so this gets a little bit frightening. But let's start up here and go clockwise. Your shampoo has perfluorochemicals to add shine to your hair. Your teddy bear is stuffed from overseas with flame retardants and pesticides. Your clothes, especially if they've been dry cleaned, can contain perfluorochemicals. Baby bottles used to contain BPA. Hopefully that's all been taken out, but if you've got older baby bottles, they'd still be there. Your mattress has flame retardants in the stuffing. Your carpet, again, flame retardants, perfluorochemicals, pesticides. TV wires and plastic contain flame retardants. Your sofa, the padding, contains, again, flame retardants, perfluorochemicals. Tennis shoes have phthalates in the bottom. Vinyl toys have phthalates. There's actually a book out there called, I think it's something called Death by Rubber Ducky, talking about how little kids put these things in their mouth and they're really ingesting that BPA, those phthalates. Your computer, again, more of those flame retardants, water bottles with BPA, fruit with pesticides that might be banned in the United States, but they're perfectly legal in other places. DDT, for example, is legal in other countries. Your tile floor, those perfluorochemicals again and phthalates. Frying pan, nonstick coating, has some chemicals in it. We used to have a macaw, one of those big parrot birds, and we learned from a person at the pet store that you cannot keep birds near your kitchen. And the reason is if you use nonstick cooking pans, those perfluorochemicals that come off will kill your bird. And we're talking about a pretty large bird here. Milk contains dioxins and flame retardants. Dioxins again are one of those fat solubles, and so it gets into the milk, which is a fatty substance inside the cow, and then it gets passed on to you and into your fat cells. Food contains BPA, hairspray phthalates, perfume phthalates, nail polish, those phthalates again, and perfluorochemicals. And we'll see another list when we get to the pollution chapter of some other ways that your house can be harmful. But this is some serious stuff going on right inside of your house. So the precautionary principle, I know we've talked about before, is the idea that we should consider something harmful until proven safe. It's a very un-American idea because we like to think you're innocent until proven guilty. But a lot of people want to adopt this, and this is what the EU does, is they say that chemicals have to be proven to be completely safe before they're allowed on the market, instead of what we do here, which is we allow things until we discover that they're actually dangerous. In 2000, there was a global treaty to ban or phase out what's called the dirty dozen. And so we have started to see some things get phased out, again, like the BPA. We've seen CFCs phased out even before 2000. And so there are some areas of progress occurring. And your final picture is just too cute for words. Baby platypi, they are poisonous, so it goes along with our whole toxins thing, but they're too cute.